check. Am I going crazy? I don't know. So our most important unit, that's the mole. A mole is defined as the number equal to the number of carbon atoms in exactly 12 grams of pure carbon-12. It is also 6.022 times 10 to the 23rd of anything. It is also called Avogadro's number. And it is sometimes given the symbol Na, so it'll be an uppercase N and with a subscript uppercase A. 1 mole of a substance contains 6.022 times 10 to the 23rd units of that substance. So if you're talking about something like NaCl, right, 1 mole of sodium chloride will contain 6.022 times 10 to the 23rd formula units. Formula? I was going to write FU and then realized that would be a little rude. Formula units. Or if it's something like H2O, right, it'd be molecules. Right? Molecules. Right? So 6.022 times 10 to the 23rd of anything is 1 mole's worth of that thing. So a sample of a natural element with a mass equal to that element's atomic mass expressed in grams contains 1 mole. So this is just saying that atomic mass on your periodic table, right, it's got units of AMUs, right, or they're using U, or sometimes you will see Daltons. It means that practically speaking, because 1 mole of carbon-12 has 12 atomic mass units, and it's going to weigh 12 grams, it's also going to have units of grams per mole. So 6.022 times 10 to the 23rd atoms of aluminum will weigh 26.98 grams, which means that the atomic mass of aluminum is 26.98 Daltons, or 26.98 grams per mole. This gives us a convenient conversion factor. And so remember all the way back to video number 1 or 2 when I said that practically speaking, what we're going to be doing operationally when we're solving a lot of these chemistry problems is looking at conversion factors. Right? And so here we've got one that'll let us go back and forth between grams and moles. If I multiply by our atomic mass, I'm going to go from moles into grams. If I'm going to divide grams by our atomic mass, I'm going to go into moles. There's a divide into moles mnemonic that you can use too, because oftentimes if you're doing that division, it brings you into moles. So let's look at an example. Determining the mass of a sample of atoms. Americium is an American, and it's the most American of American elements. It's got a party in the front. It's got a party in the front and the back. It's the element that does not occur naturally. It can be made in very small amounts in a device known as a particle accelerator. You probably have a sample of americium somewhere nearby because these guys are also found in smoke detectors. Right? So one of the things that one of the processes that they'll have for a smoke detector is there'll be this sample of americium that's giving off some particles because it's going through radioactive decay, and you'll have some sort of sensor over here, and the sensor's expecting a fairly regular input, but then when smoke comes along, it kind of breaks that circuit, and it goes, hey, something has stopped this, I've got a fire. You compute the mass in grams of a sample of americium containing 6 atoms. So what are we given? We're given 6 atoms. We want to stop at, so what is the mass in grams? That's where we're going to stop. This is what we've been given, is 6 atoms. We need our conversion factor, so we're going from grams into moles. We're going to need our molecular mass, or our atomic mass. Right. So our information is needed. We've got 6 americium atoms. The mass of one atom is 243 units, or 1 mole of atoms. Right, is going to be equal to 243 grams. So to determine the mass of 6 atoms, first thing we need to go is we're going to go from atoms to moles, right? And then you've probably already figured out that step 2 is going from moles into grams. So we're going to go from our 6 atoms. We've got You're doing it goofy. All right, 243.6 units per atom. It's going to give us 1.463 units, atomic mass units. Then they're going to use Avogadro's number. The math does not care which way you do this. For me, logically, it makes way more sense to go, I'm going from atoms, right? And then I'm going to go to moles. And then I'm going to go to grams. Right? They went from atoms into molar mass, and then they used Avogadro's number. So then they got that 6.02 times 10 to the 23rd units is going to be 1 gram. They're going to multiply by Avogadro's number, and then to determine the mass of the 6 americium atoms, they're going to go 4.6 times 10 to the 3rd units times, for every 1 gram, there is 6.022 times 10 to the 23rd units, atomic mass units, giving you 2.42 times 10 to the minus 21 grams. Right? So do this double check, right? You've got 6 atoms. Do you expect 6 atoms to weigh a lot? No, right? I've got a very small number over here, so this makes sense. Do I expect it to be slightly bigger than times 10 to the minus 23rd? Yes. If I had hydrogen, which was 1, or not even hydrogen, just a hydrogen nucleus, which would be 1 atomic mass unit, it would be 6.02 times 10 to the 23rd. This guy's got 6 atoms, right? So it's going to be bigger. Its atomic mass is bigger. So you're going to expect some more grams than 6.02 times 10 to the 23rd, right? Even the lowest end, like if you did hydrogen or helium, right? Hydrogen's going to clock in at about 2 atomic mass units. Your 1 mole, that the 1 atom of hydrogen is going to be like 2 times 10 to the 23rd. So it's in our reasonable ballpark for what makes the same number there. The molar mass of our compound is the mass of 1 mole of the compound measured in grams, traditionally called the molecular weight. The reason why it's not called molecular weight is that mass is a better term, right? It should be called molecular mass. Molecular weight has stuck around because that is traditionally something you measure, but weight depends on the gravitational constant that you're working with. So your weight will be different on the moon versus on here versus on Jupiter. Your mass will be constant. So mass is a universal constant. So mass is a better term. Weight has stuck around for historical reasons. I will sometimes do MW for molecular weight. Really, it should be MM. The problem is that we have a lot of things in chemistry, like our prefixes being M, right? So it gets confusing. Well, did you mean millimeters? Did you mean molar? Did you mean molal? We got a whole lot of things that have an M abbreviation. So calling it MW is sometimes a little bit less ambiguous, but keep in mind that it is a mass, not a molecular weight. Our formula unit is for compounds that do not contain molecules, right? So these guys are things that are ionic, right? Our ionic compounds, or our covalent network solids, like diamond network solids. Right? So sodium chloride, right? You can't say, here is a single sodium chloride molecule because it exists in this big lattice. Same thing with our calcium carbonate. But for one of those formula units within that repeating crystal structure, it's going to be NaCl. And we sure as heck can figure out what the molecular weight or molecular mass is for a given formula unit. So, for example, let's calculate the molar mass on juglone, not to be confused with the Insane Clown Posse fan base, the Juggalos. The juglone is just a dye known for centuries. It's produced from the husks of black walnuts. So if you get something that like is a walnut stained or a walnut piece of furniture, oftentimes that is taking a material that you take the husks of walnuts, which stain, and you make a stain out of that. The wood itself may not actually be walnut wood. So if you talk about something that's a walnut piece of furniture, May not be walnut. Walnuts are really bad if you grow tomatoes. If you got a tomato plant and a walnut tree nearby, and your tomato plants are not thriving, it's because of that walnut. It's a natural herbicide or weed killer. Right, bad for your tomatoes, that kills competitive plants around the black walnut tree but does not affect grass and other non-competitive plants. The formula for juglone is C10H6O3. We want to calculate the molar mass of our juglone. And we've got another example where we got a sample of 1.56 times 10 to the minus 2 grams of pure juglone that was extracted from black walnut husks. How many moles of juglone does this sample represent? All right, so we've got two things. Calculate the molar mass, and then, given this, how many moles does it represent? So one, we got to figure out our molecular weight or molecular mass, and two, we're going from grams into moles using that molar mass. So for part A, all you got to do for these is add up the atomic weights of each of those atoms. So you got 10 carbons, right? So you're going to do 10. Right, there's my 10. And then the carbon is going to be 12.01. You look that guy up off the periodic table, 120.1 grams. You got six hydrogens. You're going to do 6, right, times the 1.08. This is going to give you 6.048. And then you got 3 oxygens. So you're going to do 3 times the molar mass of oxygen, 16, 48 grams. And so all you do is you multiply each element by its molecular mass and the number of elements. You look within your molecular formula, multiply, add them all up. You end up with 174.1 grams. Right, so that means that the molar mass of juglone is 174.1 grams per mole. Right? And this is our handy-dandy little conversion factor that we're going to use in step B. So the mass of 1 mole of this compound is 174.1 grams. Therefore, our 1.56 times 10 to the minus 2 grams is a lot less than a mole. Right, just kind of looking at orders of magnitude, this guy's going to be 10 to the 2. Right, this guy down here is 10 to the minus 2. So we're just kind of order of magnitude guessing. It's going to be about times 10 to the minus 4. Right, just kind of guessing. The exact fraction of a mole can be determined as follows. We're going to take our 1.56 grams of juglone. We're going to multiply by the inverse of the molar mass. We're going to divide. Right, so we're doing 174.16 grams. Our grams cancel out. Notice we've included the molecular species as well, because that's part of our conversion factor. We're going to be left with units of moles, and we end up with 8.96 times 10 to the minus 5, which is pretty darn close to our original estimate of 1 times 10 to the minus 4, right? So our answer is within the ballpark. It's not going to be a lot of moles, right? And we're seeing not a lot of moles happening.